Hi guys, in this video I'm going to talk about the conversion of a convolutional neural network from TensorFlow to Caffe. To do this, the network architecture has to be recreated in Caffe, the weights and biases have to be exported out of TensorFlow, and then the network has to be adapted and imported to Caffe. I'm aware that this problem might not be very common, but I had to do it during my bachelor thesis and maybe someone else has to do it as well. So I thought I'd just document what I did to save someone else the struggle of the conversion. So yeah, let's get started. The first thing we have to do is the recreation of the network architecture in Caffe. One thing beforehand, I used TensorFlow as a higher level API for TensorFlow, and I will do so in this video as well. I'll put a link in the description, but if you don't want to use TensorFlow, that's fine as well. The conversion should work in native TensorFlow or with other wrappers as well, but the export of the weights and biases will be a little different, and you're gonna have to work that out for yourself. Okay, so the model I'll convert in this video is the VGGNet, the VGGNet 19 to be exact. The VGGNet is the winner of the ImageNet Challenge 2014, and if we take a look at their paper, we can see the architecture they've used. As mentioned before, I'll recreate the VGGNet 19. We can see that it consists of convolutional layers, pooling layers, and fully connected layers. Here's a visualization that might be a little bit easier to understand. I will now create the network architecture in TensorFlow. If you're familiar with TensorFlow already, you can skip this part. There will be a timestamp on the screen. Alright, we're in Eclipse now. I've already created a project. The first thing I'm going to do is create a new script. I'm going to call it model. This is the file where we will save the architecture of the VGGNet. We have to import some things from TensorFlow, and those are input data. This is a definition where we can feed the network. Conv2d, this is the convolutional layer. Max pooling, fully connected layers, dropout, momentum, and DNN. DNN means deep neural network. We can start defining the network now. I'm gonna call it VGGNet 19. The input parameters are the width and the height of the input image. Normally you would use more parameters like the learning rate, data augmentation, and so on. But since we can use the initialized architecture of the network to compare the networks and we don't have to train it, I'm not gonna use additional parameters. Okay, the first layer of the network is the input data layer. The first thing we have to define is the shape of the input data. The first entry of the shape is none. This refers to the batch size, and as the batch size is not fixed, I'm giving it a variable that's not fixed as well. Then come the height and width of the input image. You have to use it in this order. If you don't use it in this order, you're gonna get mistakes or bad results, especially if you use non-square images as inputs. And the last entry are the channels of the image. We use an RGB image, so we have 3 channels. And the name of the layer is input. Okay, looking at the next layer of the VGGNet, we can see that it's a convolutional layer with 64 filters, a 3x3 filter size, a stride of 1, and ReLU as an activation function. And what cannot be seen here, but is still true, is that the VGGNet uses weight decay with L2 regularization, and the multiplier is set to 5 times 10 to the power of -4. So I'm just going to define that. We use the conv2d because we do convolution. To extend the network, we have to give it as a parameter, so it's like I equals I plus 1 in a sense. Next thing is the number of filters, then the kernel or filter size, the activation, ReLU, and then the regularizer, hard word, regularizer, and then the weight decay, 5 times, right, like this. Okay, the next layer is defined just like the previous one, so I'm just gonna copy this. And then comes the max pooling layer. Again, we have to give the network as the first parameter to extend it. And as we can see, the max pooling uses a 2x2 filter with a stride of 2. So I'm just gonna define that. The first parameter is the filter size, and then come the strides. Alright, the next layers are kind of similar to the layers that we've described already, so I'm not gonna talk about everything, I'm just gonna write it and you can follow. I'm just gonna change the filter sizes basically, so I'll see you in a bit. Okay, now the network is defined up to the first fully connected layer, and to define that, that's quite simple as well. We're just gonna use the full connected input or field, whatever. Give the network again. Then we define the number of units in the layer, the activation function, and then the weight decay. Actually, I'm not quite sure where the weight decay is used. If you read their paper, it's not so obvious, I think. Here's the text. If you know what the correct use of weight decay in the VGGNet is, you can tell me. Alright. After the fully connected layer comes dropout. Give the network to extend it. And then we can define the probability with which unit will drop out. And after that are some more fully connected and dropout layers. And then comes the final layer. We do not use ReLU here, but softmux. And the number of classes. In the case of VGG, there are 1,000 classes. Then we have to define our optimizer. VGNet uses momentum with. Alright, so I have to give the lang rate here, but I'm just gonna use a dummy variable, so I can just use 0 here. It doesn't matter. I'm not gonna use it. And the momentum was equal to 0.9. Then we have to define the regression layer. This is where we define the optimizer or give it to the network, and also define the loss function. Give the network first to extend it, define the optimizer, and then the loss function. We use the categorical cross entropy here. And the name, I'm gonna call it targets. You could also name it labels or whatever you want. And then we define the model. This is like a package to put in all the things we've defined before. So the first thing I'm gonna give it is the network, then checkpoint path. This is I think where the model gets saved during training, because if your computer crashes or you run out of memory or something like that, the model will be saved here. Then there are some more the number of checkpoints you want to have, the verbosity of the TensorBoard. I'm not sure if you have to give these parameters. I'm just used to giving them, so I'm just gonna do it. And then the directory where the logs will be saved. Did I not import regression? No, I didn't. Alright, just gonna do that. and then I'm just gonna return the model. So if I call the function, it will give me the whole model. Okay, the network is fully defined now in TensorFlow. Now we have to recreate this architecture in Caffe. I'm using a virtual machine to use Caffe, so don't be confused why we are in Linux now. And what we have to do is create a proto-text. This is a file where Caffe saves its model architectures. I'm just going to call it VGGNet19 again. And the process that has to happen is in general the same that we did in TensorFlow as well. It has just a different syntax. The first thing I'm going to do is name the model. I'm just going to call it VGG and then define the first layer. It's the input data layer, just like in TensorFlow. I also have to define the shape of the layer, the shape of the input data, I mean. It's a little different than in TensorFlow. The first parameter is the batch size. We just test one image to see if the networks have the same results. So I'm just going to use the one. Then comes the number of channels. And this is the height. And then the width. This is important if you use non-square images. Okay, the first layer is the convolutional layer, just like in TensorFlow. I'm going to give it a name and define its type, convolution. And then in Caffe you always have to define the bottom and the top layer of the network. The bottom layer is always the one that feeds the current layer, and the top layer is where the data of this layer will be presented. I'm not quite sure what the top layer actually does. I'm not so familiar with Caffe, but in general, it's just the layer name of the current layer. Okay, I'm also gonna have to define some convolution parameters. The number of outputs. This is equal to the number of filters in the layer, the kernel size or filter size, the stride, and the padding. You have to be careful in Caffe. Caffe does not support asymmetric padding, and in some cases you will end up with asymmetric padding in TensorFlow or TensorFlow, which supports asymmetric padding, and then you want to recreate the model in Caffe, but you can't because asymmetric padding is not supported. So be careful with that. And the ReLU activation function has its own layer. The name is ReLU1. Type is ReLU. The bottom and the top are equal in this case. It's just the convolution layer we want to use the activation function on. Alright, the next layer is just another convolution layer, but contrary to TensorFlow, I have to make some changes. I have to change the name, the bottom layer, the top layer, the convolution parameters stay the same. The ReLU gets a new name, and the bottom top change as well from convolution 1 to convolution 2. Then comes the max pooling layer. It's defined like this. The name is max pooling. The type is pooling. The bottom is conv2. And the top is max pool 1. And the pooling parameters are the pooling type. In our case, it's max. Could also be average pooling or something else. The kernel size is 2, and the stride is also 2. Alright, the definition of the ongoing layers is kind of the same, just like in TensorFlow, only the number of filters change, and I'm sure you don't want to see me type all this out, so I'm just gonna write it down, speed up the process, and come back when I'm at the fully connected layers. Okay, I'm done with the definition of the network until the last max boom layer. Don't worry if you can't follow the tempo of the sped up footage. The code will be on GitHub. Alright, now I have to only define the fully connected layers. They are defined like this. Name, I just call them FC1. Type, Caffe calls them inner product. Bottom is max pool 5 in this case. Top is just FC1. And the inner product parameters are just the number of units or number of outputs, 4096. And don't forget the activation function. It's ReLU 17 already. Bottom FC1 and top as well. Okay, then there follows just another layer of fully connected. Just gonna do this real quick. And another layer, the last layer of the network. Oops. It has only 1000 outputs and it doesn't have ReLU as an activation function, but softmax. Alright, that's it. We've recreated the architecture of the VGGNet in Caffe. The next step is to export the weights and biases out of the network that has been initialized in TensorFlow, but I will cut the video here and make it part 2 because I don't want the video to be too long. So see you in the next part.